Hello, this is Michael Millard for Real-Time Rendering Assignment 5, and this is my demonstration video for my project, which was entitled An Approximate Image-Space Approach for Interactive Refraction. This paper was written by Chris Wyman from the University of Iowa, and he presented it at his 2005 SIGGRAPH conference. So as the title suggests, this is a refraction project. So I've implemented a refraction through one surface implementation, which is very similar to what I believe was assignment 2. I have then implemented what is based on Chris Wyman's approach, which is refraction through two surfaces. And this accounts for it traces the ray through, and then it bends on its way out of the model as well to create a more physically accurate representation of how light interacts with the medium through two surfaces. I've got 5 different models that I've used to test for this assignment, and I've also implemented a ray trace approach in OpenGL, which is a 4-bounce path tracer. It's very slow, so I haven't included it in this representation, but I will show it at the end as it slows my laptop down quite significantly. So to demonstrate the one surface approach, this is quite a complicated model, this Buddha model right here, which is why I've included it, because Chris Wyman's approach is most effective for convex objects, where the light enters one side and exits the outside. There are only 2 real surfaces where the light goes in and out. It performs less well for concave objects because the light rays follow a far more complicated path as it transmits through the medium. So for the one surface approach, I'll show the sphere. This is a good example of showing why for something that is as curved as a sphere, the one surface refraction performs quite poorly visually. You can see that it's got a very, very distorted result. And this is because this is simply computing a once-off refraction at every point in the sphere and indexing out of the skybox without accounting for the bending as the ray exits the sphere. So this is accounted for in Chris Wyman's approach, and it gives a far more crisp result. And when I run the ray tracing implementation at the end to compare this with, I will show you how this approach that shows the background upside down is a far more impressive result when you're keeping the index of refraction the same. So right now I'm testing all of my models with an IOR of 1.5. relative to the air, which is an IOR of 1, and that just makes sure that the comparisons drawn are fair. So if I change to the ray traced implementation now, which is just over here. So as I mentioned, the ray traced implementation is implemented in this fragment shader over here. It's inspired by, I hope I say this correctly, the Millard-Trumbull ray triangle intersection. And I've rendered a full screen triangle that is deliberately too large such that the entire screen space fits inside the triangle. And then at every pixel in the screen space, I cast a ray to each triangle in the mesh of the object, and I compute whether that ray intersects that said triangle. And then I keep track of the closest triangle to where that ray originated from, and I do this for a maximum of what I believe is, I've defined max bounces at 4. So it will trace the ray through the object for 4 bounces, moving the origin of each hit to the where it hit, and then casting a new ray again from that origin. And in that way, you can create a physically accurate representation of what the model in that skybox would truly look like. And that's the visual ground truth that I compare against in my report. So this will slow my laptop down quite a lot, but I've chosen Suzanne the monkey as the model to be rendered, which is the lowest polygon count and therefore does perform the best. So it's a very slow, but I can slowly change the IOR, and this is a form of real-time ray tracing with acceptable performance because my implementation of ray tracing isn't optimized at all. It's rather to serve as a ground truth measure. So I wanted to demonstrate the sphere specifically though, because as you remember, See, this is with an IOR of 1.5. The single surface refraction had a very distorted result, whereas the two surface refraction proposed by Wyman had a result that looked very, very similar to this. And that's an excellent example of how a convex object such as a sphere is able to be very well simulated using Wyman's approach. And what is most important of this implementation is the fact that Chris Wyman's approach in my project achieved more than 300 frames per second, which is an excellent real-time rendering result. Whereas, as you can see, my mouse is extremely laggy in this real-time ray trace implementation, getting single-digit frames per second, if even. And that is a very, very important result in that you can create what's almost a physically realistic representation of the scene with Wyman's approach, and at significantly better frame rates that are actually acceptable for real, not even acceptable, impressive for real-time applications, with over 300 frames per second in most instances. So I'll just close this application one more time and go back to what the sphere looked like in the refraction OpenGL implementation, just so you can get one final comparison visually. So I'll just change the museum with the sphere. So as I was saying, the sphere is very, very distorted. But if I change to Chris Wyman's approach, you can see there are still visual artifacts, but the physical structure of the refraction is incredibly, it resembles the ray traced implementation very closely. And this is running at north of 300 frames per second, which is a very impressive result. So thank you very much. All of my code that I've used to implement in this assignment is attached to my submission. And thank you.